The concept of linear combinations is central to linear algebra and related fields of mathematics. Most of this article deals with linear combinations in the context of a vector space over a field, with some generalizations given at the end of the article. Definition. Suppose that K is a field and V is a vector space over K. As usual, we call elements of V vectors and call elements of K scalars. If V1, Vn are vectors and A1 and are scalars, then the linear combination of those vectors with those scalars as coefficients is. There is some ambiguity in the use of the term linear combination as to whether it refers to the expression or to its value. In most cases the value is emphasized, like in the assertion, the set of all linear combinations of E1, Vn always forms a subspace. However, one could also say two different linear combinations can have the same value, in which case the expression must have been meant. The subtle difference between these uses is the essence of the notion of linear dependence. A family F of vectors is linearly independent precisely if any linear combination of the vectors in F is uniquely so. In any case, even when viewed as expressions, all that matters about a linear combination is the coefficient of each vi. Trivial modifications such as permuting the terms or adding terms with zero coefficient do not give distinct linear combinations. In a given situation, K and V may be specified explicitly, or they may be obvious from context. In that case, we often speak of a linear combination of the vectors v1, vn, with the coefficients unspecified. Or, if S is a subset of V, we may speak of a linear combination of vectors in S, where both the coefficients and the vectors are unspecified, except that the vectors must belong to the set S. Finally, we may speak simply of a linear combination, where nothing is specified. In this case one is probably referring to the expression, since every vector in V is certainly the value of some linear combination. Note that by definition, a linear combination involves only finitely many vectors. However, the set S that the vectors are taken from can still be infinite. Each individual linear combination will only involve finitely many vectors. Also, there is no reason that n cannot be zero. In that case, we declare by convention that the result of the linear combination is the zero vector in V. Examples and counterexamples. Euclidean vectors. Let the field K be the set R of real numbers, and let the vector space V be the Euclidean space R3. Consider the vectors E1 equals, E2 equals and E3 equals. Then any vector in R3 is a linear combination of E1, E2 and E3. To see that this is so, take an arbitrary vector in R3, and write. Consider the vectors f and g defined by f equals EIT and g equals E minus it. Some linear combinations of f and g are. On the other hand, the constant function 3 is not a linear combination of f and g. To see this, suppose that 3 could be written as a linear combination of EIT and E minus it. This means that there would exist complex scalars A and B such that AEIT plus B minus it equals 3 for all real numbers t. Setting t equals 0 and t equals pi gives the equations A plus B equals 3 and A plus B equals minus 3, and clearly this cannot happen. See Euler's identity. Polynomials. Let K be R, C, or any field, and let V be the set P of all polynomials with coefficients taken from the field K. Consider the vectors P1 equals 1, P2 equals x plus 1, and P3 equals x2 plus x plus 1. Is the polynomial x2 minus 1 a linear combination of P1, P2, and P3? To find out, consider an arbitrary linear combination of these vectors and try to see when it equals the desired vector x2 minus 1. Picking arbitrary coefficients a1, a2, and a3, we want multiplying the polynomials out. This means and collecting like powers of x. We get two polynomials are equal if and only if their corresponding coefficients are equal. So we can conclude this system of linear equations can easily be solved. First, the first equation simply says that a3 is 1. Knowing that, we can solve the second equation for a2, which comes out to -1. Finally, the last equation tells us that a1 is also -1. Therefore, the only possible way to get a linear combination is with these coefficients. Indeed, so x2 minus 1 is a linear combination of p1, p2, and p3. On the other hand, what about the polynomial x3 minus 1? If we try to make this vector a linear combination of p1, p2, and p3, then following the same process as before, we'll get the equation. However, when we set corresponding coefficients equal in this case, the equation for x3 is which is always false. Therefore, there is no way for this to work, and x3 minus 1 is not a linear combination of p1, p2, and p3. The linear span. Main article. Linear span. Take an arbitrary field K, and arbitrary vector space V, and let V1, Vn be vectors. It's interesting to consider the set of all linear combinations of these vectors. This set is called the linear span of the vectors, say S equals V1, Vn. We write the span of S as span or SP. Linear independence. For some sets of vectors V1, Vn, a single vector can be written in two different ways as a linear combination of them. Equivalently, by subtracting these, but not conical or affine combinations. And positive measures are closed under conical combination but not affine or linear, hence one defines signed measures as the linear closure. Linear and affine combinations can be defined over any field, but conical and convex combination require a notion of positive, and hence can only be defined over an ordered field, generally the real numbers. If one allows only scalar multiplication, not addition, one obtains a cone. One often restricts the definition to only allowing multiplication by positive scalars. All of these concepts are usually defined as subsets of an ambient vector space, rather than being axiomatized independently. Opera theory. More abstractly, in the language of opera theory, one can consider vector spaces to be algebras over the operad, which parametrizes linear combinations. The vector, for instance, corresponds to the linear combination. Similarly, one can consider affine combinations, conical combinations, and convex combinations to correspond to the suboperads where the terms sum to 1. The terms are all non-negative, or both, respectively. Graphically, these are the infinite affine hyperplane, the infinite hyperoctant, and the infinite simplex. This formalizes what is meant by being or the standard simplex being model spaces, and such observations as that every bounded convex polytope is the image of a simplex. Here suboperas correspond to more restricted operations and thus more general theories. From this point of view, we can think of linear combinations as the most general sort of operation on a vector space, saying that a vector space is an algebra over the operad of linear combinations is precisely the statement that all possible algebraic operations in a vector space are linear combinations. The basic operations of addition and scalar multiplication, together with the existence of an additive identity and additive inverses, cannot be combined in any more complicated way than the generic linear combination. The basic operations are a generating set for the operad of all linear combinations. Ultimately, this fact lies at the heart of the usefulness of linear combinations in the study of vector spaces. Generalizations. If V is a topological vector space, then there may be a way to make sense of certain infinite linear combinations, using the topology of V. For example, we might be able to speak of A1V1 plus A2V2 plus A3V3 plus, going on forever. Such infinite linear combinations do not always make sense. We call them convergent when they do. Allowing more linear combinations in this case can also lead to a different concept of span, linear independence, and bases. The articles on the various flavors of topological vector spaces go into more detail about these. If K is a commutative ring instead of a field, then everything that has been said above about linear combinations generalizes to this case without change. The only difference is that we call spaces like this V-modules instead of vector spaces. If K is a non-commutative ring, then the concept still generalizes, with one caveat. Since modules over non-commutative rings come in left and right versions, our linear combinations may also come in either of these versions, whatever is appropriate for the given module. This is simply a matter of doing scalar multiplication on the correct side. A more complicated twist comes when V is a bimodule over two rings, KL and KR. In that case, the most general linear combination looks like where A1 and belong to KL, B1, Bn belong to KR, and V1, Vn belong to V.